We're talking about why your robot still feels slow despite having massive computing power. The problem is not your code or your sensors. It is the fundamental architecture of every computer on the planet. By the end of this, you will understand why the industry is stuck in a physical bottleneck and why the only path to true Star Trek autonomy lies in a completely different type of hardware. Imagine a factory assembly line where the workers can build a part in a millisecond, but they have to walk across the entire factory floor to get the blueprints and the raw materials. They spend 99% of their time walking and waiting. This is exactly what happens inside your computer every single second. We call this the von Neumann bottleneck. It is named after John von Neumann, the mathematician who defined the standard computer architecture in the 1950s. In this design, all data and all instructions share the same pathway to the processor. The computer must fetch an instruction, then fetch the data required to execute it, then write the result back. This sequential process creates a massive latency gap that makes real-time autonomy physically impossible with current silicon. You might wonder why we have not switched to the Harvard architecture, which separates the instruction bus from the data bus. Theoretically, this should solve the problem. A Harvard design allows the processor to fetch an instruction and read data at the exact same time. It sounds like a perfect solution for robotics, where you need to process sensor data and execute motor commands simultaneously. Yet, the industry remains locked into the von Neumann model. The reason is not a lack of innovation. It is the immense cost of rewriting the entire software ecosystem and the dominance of CMOS manufacturing standards that prioritize general-purpose flexibility over specialized throughput. Here is the thing that changes everything. The bottleneck is not just about fetching instructions, it is about the power required to move data. In modern systems, the energy cost of moving information between the processor and the memory dwarfs the energy cost of actually performing the calculation. This is known as the memory wall. When a robot tries to process a video stream or interpret complex tactile feedback, the system spends the vast majority of its power and time shuttling gigabytes of information back and forth. The processor sits idle, waiting for data to arrive. This creates a delay between perception and action that no amount of software optimization can eliminate. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the difference between a robot that reacts to a stimulus and one that thinks about it. In a von Neumann system, the robot sees an obstacle, sends the image to memory, the processor fetches the image, processes it, sends the result back to memory, and then the motor controller fetches the command. Each step introduces latency. In a biological brain, the neurons that process the visual input are the same structures that trigger the motor response. There is no shuffling of data. Information is processed where it is stored. This is the principle of in-memory computing. This is why current systems cannot achieve the seamless sensory motor loops required for true autonomy. The latency gap between sensing the world and acting on it is too wide. A robot might detect a falling object, but by the time the calculation completes, the object has already hit the ground. The sequential fetch-execute cycle creates a fundamental delay that prevents the kind of reactive behavior we see in nature. You cannot code your way out of a physical constraint. The laws of physics dictate that moving electrons across a chip takes time and consumes energy. Now consider the alternative. Neuromorphic hardware is not just an efficiency upgrade, it is a fundamental architectural necessity to escape the von Neumann bottleneck. These chips are designed to mimic the brain's structure. They are event-driven, meaning they only process information when something changes. If a sensor does not detect movement, the system consumes almost zero power. If a sudden change occurs, the relevant neurons fire immediately. This eliminates the need for a central processor to constantly poll sensors for updates. The transition to neuromorphic architectures is often framed as the only path forward for real-world robots. However, we must be intellectually honest about the current state of this technology. While the theoretical benefits are clear, the transition is not yet a market reality. We are still facing significant hurdles with simulation and software stacks. Writing code for a neuromorphic chip requires a completely different mindset than writing for a standard CPU. The tools are emerging, but they are not as mature as the decades of development we have invested in CMOS technology. There is a credibility challenge here. We cannot claim that neuromorphic hardware has already solved these bottlenecks in production. We do not have the empirical benchmarks or adoption metrics to prove that it is ready to replace every existing system tomorrow. The claim that it is the only path forward is a theoretical necessity based on the physics of the von Neumann bottleneck, not a proven market reality. The hardware exists, but the ecosystem is still in its infancy. This brings us to the critical insight. The rigidity of current designs creates a hard ceiling for robot autonomy. As long as we rely on the sequential movement of data between separate compute and storage units, we will be limited by the speed of light and the resistance of copper. We are trying to build a Star Trek future with a Star Trek past. The only way to break through this ceiling is to abandon the idea of a central brain and move toward distributed, event-driven processing where computation and memory are fused. We are standing at a crossroads. We can continue to optimize a flawed architecture until we hit the physical limits of silicon, or we can embrace a new paradigm that aligns with the physics of intelligence. The choice is not just about speed. It is about the fundamental capability of machines to exist in the real world without constant human intervention. Until we solve the data shuffling problem, robots will remain sophisticated tools rather than autonomous agents. The future of robotics depends on our ability to move beyond the von Neumann model and embrace the complexity of the brain. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.